Start recording. So I don't want to steal too much of your thunder, but just a little bit of an introduction for everybody who hasn't seen the emails I've been sending out, or is watching this later. This is Dr. Eric Coughlin. He is a Lehigh alum. He got his BS in astrophysics here, and then went on to get his PhD at UC Boulder before he became the NASA Einstein Fellow at Berkeley and then Columbia, and then the NASA Hubble and Lyman Spitzer Fellow at Princeton. And now he's doing a bunch of cool research at Syracuse as an assistant professor, which he might be able to come and tell us about next semester, right? So
Yeah, that's the hope.
that'll be exciting to hear. But for right now, if you'd like, could you tell us about maybe your undergrad and graduate career and how you decided the path of astrophysics and what you're doing now?
Yeah, I wasn't entirely sure exactly what you wanted me or how we were going to structure this. So what I ended up doing was actually just putting together a few slides
Okay.
uh, that kind of have like, in addition to my trajectory, just sort of some like suggestions and little pieces of advice. Would it be okay if I just kind of go through that? Does that seem reasonable?
Yeah,
Or
definitely.
okay, let me. Oh, can you allow me to share my screen, please?
Um, do you have to request that, or do I just make you
It just
co-host or something?
It just says host disabled participant screen sharing. So if you go down to security, oh, actually, wait a minute. Oh, weird. Okay, it just let me do it. So,
Okay.
um, okay. So can everybody see this? Yeah.
Yes.
Okay, cool. All right. Yeah. So thanks, Daniel. Yeah, thanks for the introduction. I am happy to do this, and I'm happy to talk about my sort of trajectory. And so what I thought I would do is kind of just go through so this is like, in a very condensed nutshell, pretty much exactly what Daniel just said, with the exception of the parenthetical thing at the top there, which is mostly just to say that I actually grew up very nearby Lehigh. It was actually one of the determining factors in terms of where I wanted to go. I kind of wanted to stay relatively local, at least for my undergrad, and also because Lehigh is a great school, obviously. But from right, so I finished up high school in 2007. I was at Lehigh from 2007 until 2011, where I got my Bachelor of Science in astrophysics. I then moved out west, where I was at the University of Colorado at Boulder for 5 years, where I did my PhD. And then also, let me just minimize the little sidebar up here. Sorry, my cursor disappears every time there we go. Right, and then when you do a PhD, you typically get a master's along the way. And then I did a few postdoc positions before winding up at Syracuse. So I thought what I would do is sort of just go through these kinds of steps individually. And I thought, given that the audience here consists primarily of undergraduate students and graduate students, I'm kind of going to focus mostly on the first two. So kind of my undergrad experience and just some, very brief suggestions for all of you, because at least some fraction of you are currently at the undergrad level. And then I'll spend like a good amount of time, I think, just talking about what I did and some suggestions for you in graduate school, because it's a big chunk of your life. It's also where you have or usually it's where you have a lot of personal freedom. You're free to travel and go about and do things you haven't done before. So I'll just kind of give you my personal experience in that regard. And then I'll talk, relatively briefly about postdocs, and then I'll finish on a slide about professoring. But I figured, I'll talk about the undergrad experience, I'll talk about the grad school experience, but then I feel like it probably makes sense to sort of pause in between those and take any questions, just because it kind of makes sense that way. So Okay, so right, I was at Lehigh from 2007 to 2011, where I did my BSc in astrophysics. And so Daniel already said, how did I get into astrophysics, or why did I do astrophysics? When you're picking your major, it's really important, at least it was for me, to pick something that you're passionate about. And so I technically was a mechanical engineer for about 2 weeks, when I realized I'd made a terrible mistake, and that the thing that I really wanted to do was astronomy and astrophysics. And I think a lot of people have this sort of backstory where they looked up at the stars at night and they thought that was amazing. Whereas I think I was a little bit different in that the thing I thought was most intriguing was actually the math and the physics and the application of that to astrophysical contexts, so astronomical phenomena. And that was what I really wanted to do. And I was really interested in the theory that underlies a lot of that. And so a lot of you are already physics majors, you're in society of physics students. So this is probably not really the advice that you need at this point, but for anyone who's listening to this afterward, I think it's important to choose what you're passionate about when you're deciding on your major. Um, it's also important to have a life while you're an undergrad. So taking courses is the main emphasis. But you want to do things, you want to have a life at the same time, you want to have fun. So to give you a sense of perspective, when I was in undergrad, one of the big things was Halo 3. I don't even know what Halo they're on now. It's like 5 maybe. Call of Duty. I played Super Smash Brothers a whole lot with my friends. Played Ultimate Frisbee, disc golf. And I drove out to see, I don't know if anybody knows, this Lebanon Valley College. It's a really small college out near Hershey. So I would drive out there. She's now actually my wife. So it's just kind of important to realize that there are things outside of schoolwork to do and to kind of enable you to retain some sense of sanity while you're trying to get the best grades you can. Things are, tough at the beginning in undergrad. And for a lot of people, it's your first time kind of away from home, right? I mean, for me, that was my experience. As I said, I wanted to stay local. And then after about 2 weeks, I realized how much better it was living on my own than with my parents. And so a lot of you will probably have that same experience. Another thing, and this is something that now kind of on the other side as a professor, you kind of remember how much quicker the college pace is compared to the high school pace. You're essentially cramming the same amount of material or more into half the time that you would get it in high school. And there's always kind of a sense of imposter syndrome. And so for me, I come from a very non-academic family. So my parents, I think my dad had a business degree from like a 2-year school. My mom maybe did like a semester of community college before she decided that wasn't her thing. And nobody in my family, as far as I know, has a PhD, let alone does science for a living. And so a lot of that for me was kind of just figuring out what I needed to do to get into this position and feeling like, you don't quite belong. And so the important thing to realize is that those sorts of feelings are natural, and everybody kind of experiences that to some degree. So it's tough for these reasons in the beginning, but as you go on, you get more used to it, and it becomes a really enjoyable experience. Is why one of the reasons I think it's really important to experience undergrad is that it's kind of the first stepping stone toward becoming an adult, and it's a really it's kind of just a progression in many ways, and it's not just about learning new information. So kind of the trajectory that I want to take in this talk is to be mostly along the lines of an academic career that you're thinking about. A lot of what I'm going to say is also applicable in more industry types of settings, and I can come back to that at the very end if people have questions. I don't know that side of things nearly as well as I know the academic one. But if you're thinking about going to grad school as an undergraduate student, years 2 to 3 to year 4, right, when you're starting to graduate and thinking about graduating, it's a good idea to start thinking about getting into some research. So as physics majors. Physics is a giant field, right? Astrophysics is one very small subset of the things you can do as a scientist. So think about kind of what you really want to do, again, with the same mindset of what you're passionate about, and think about the science that you could actually do as a career. Um, and once you're kind of settled on that and you think you might know what you want to do, try to find some research active faculty that are doing research in that area that you're really interested in. And, just it at this point, it's kind of on you to reach out to them and say, hey, I'm really interested in the research that you do. Do you need, some sort of research assistant? I would really like to help out with any potential projects that you have. And so for me, I did an REU with, yeah, this is my next bullet point. So another aspect of this that's very much related are what are called REUs, or research experiences for undergraduates. And so these are NSF sponsored, correspondingly paid research positions that are usually over the summer, but sometimes there are actually semester-based ones where you'll go to a different institution or occasionally the same institution and do a research project for something like 6 weeks. And so I did one of these as an undergraduate student. I think the summer between sophomore and junior year, I actually worked with George McCluskey at Lehigh. George, I think, has since retired. I'm not sure if anyone listening right now knows who he is, but he's a really fantastic guy. He taught a lot of the astronomy classes when I was there. And then during my junior year and in at least part of my senior year, I actually worked with Ginny McSwain, who I think most of you know. She's still in the department. Both of those projects were actually more observational. And as I said, or at least alluded to, I'm very much of a theorist. So I didn't really follow that kind of specific path in terms of the research that I did. But the important part, and I think the important part for most people, is not so much the exact research that you do, but it's actually more figuring out how to do research and actually getting skills. So in the beginning, right, it can definitely be overwhelming and you have no idea what the heck you're doing, and that's natural. So try not to get too overwhelmed. And this is something where now again, kind of being on the other side of this, I kind of hesitate a little bit with getting undergraduate students into research very, very early because it can be very overwhelming. But again, I think the benefit of this is not even necessarily so much the research itself, but more just like the practical skills that you learn. And so something that I figured out how to do when I was doing research, and that's been indispensable to me for forevermore, essentially, is figuring out how to learn stuff on your own. So Googling and using Wikipedia. I to this day constantly I'm Googling things when my code crashes, something breaks, I don't know what the heck's wrong, right? You just throw it into Google. And that is actually a skill that you pick up and you learn, and you figure out that not everything is in a textbook. And the other thing is computation. And so I think most of you probably have had a programming class of some kind. You probably used Python. So that was not actually nearly as heavily emphasized back when I was in undergrad. And so doing research, I really figured out how to use things like the command line. LaTeX is another really useful tool for writing professional looking manuscripts. A lot of journals will have what are called class files where you can actually compile your own PDF that looks like a professional published paper, which is nice. And then Mathematica. So Mathematica is actually not so big in the astronomy community. A lot of people, or at least a fraction of people, still use something called IDL, which is a fairly archaic language that you have to pay for. But a lot of people still use it, especially in certain regimes of astronomy and astrophysics. But Mathematica, I absolutely love, and I've been using it since day one. And to prove that, this is a picture of me in 2010-ish. Sorry, there's like a little thing at the top. Yeah, I'll close out in a second. So this is me during my REU. And if you stare closely at that computer screen, there's actually a tiny little Mathematica symbol up there. And so this is, part of what I was using when I was doing my research. And so there I'm, looking very, I don't know, sprightly. I'm really excited about the research that I'm doing. And nowadays, this is more my standard demeanor. My wife and I have 3 kids who keep us twins among the 3. So they keep us pretty busy. So that was sort of, sorry, one second. Let me just There's a stupid little thing at the top here. That was kind of most of what I was going to say about undergrad in particular. I think it makes sense to maybe pause just for, a minute or two, and I can answer any questions that anybody has.
I know I do have a question. Were there any like, I guess, resources or things that you wish you had at the undergrad level, or you wish you had taken advantage of at the undergrad level that would have helped you now?
So what I will say is that my trajectory from undergrad to grad school to where I'm finally landed now as a faculty member is a little bit idiosyncratic compared to what a lot of people do in astronomy, because I started at Lehigh, obviously, and Lehigh has a physics program, but there's no a physics department, and there's an astrophysics major, but there's no astronomy department, right? So it's Ginny and Josh and a few other people who do astronomy within the department, but then most of the emphasis of the astrophysics degree is actually on physics. And so like when you do the Astro BS, you take like, at least 90% of the classes that you would otherwise take for the physics BS. And that was actually extraordinarily useful for me in graduate school, actually. So I went from a physics program undergrad education to an astronomy PhD program at Colorado. And there, the kind of terminology and the phenomenology was very different from what I had been kind of thinking about. And there's just a lot of jargon that you have to get used to. So if you do astronomy, you'll get to know what I'm talking about very quickly. Even the units that we use are different. But I was like excellently prepared, I would say, in terms of like my physics underpinnings because of the classes that I took. And so I had like, E&M1, E&M2, nuclear physics. I had like, I think I took graduate quantum with Gary DeLeo when he was still around, and that was like an amazing, like just fantastic class. So learned all about like Clebsch-Gordon coefficients, and all of those things kind of appear again, but very much in an applied setting. And so when you have the underlying kind of tools to analyze that, it makes kind of the interpretation much more readily available, right? And it's something that you can achieve much more quickly. Um, in terms of like what I wish I would have had, I think like it would have been beneficial for me to get into programming a little bit earlier. Because as I mentioned, that was sort of something that I kind of missed out on. As being my generation, I guess, I grew up with like Windows 95. But at the time and when I was in high school, programming and computation was just not nearly as heavily emphasized as it is today. And so it was kind of a big learning hurdle when I got to grad school and I started having to do research. And you realize pretty quickly that a lot of the theoretical training that you receive is on, it's all very useful in a mathematical sense, learning how to solve like ODEs and whatever. But usually the problems that you're solving are very different, and the kind of solving strategies are very different from what you end up employing in grad school. And so like, in undergrad, you're learning from a textbook, the professor's standing at the front of the classroom if you learn in a traditional sense like I did. And it's kind of like everything is sort of prepackaged, and you're using known methods to apply to solve some problem, right? So it's expected you're going to use some method to solve some problem, and the universe doesn't tell you what method to use. And so that's part of the problem. And so a lot of times you just can't do things analytically, and so you're really forced to rely on low level computation at least, and that's something that like Mathematica is like readily equipped to do. So I think like, I kind of forced myself to learn Mathematica, and I really got into the command line and stuff because I thought it was really cool. But I could have used a little bit more, I think, like kind of formal training in more high level programming and computation. But you pick it up eventually. Um, yeah, I can't really think of anything else right now at the top of my head, but if I think of something else, I'll chime in about it.
Okay.
Are there any other questions?
Yeah, I also had sorry. Okay, sorry about that. Why am I?
You gotta turn off the audio.
Okay, is it okay? I think that's good.
Yeah, no, you're
Sorry
good.
about that. I think it was first it was funny when you showed the photo of physics lounge because it still looks the same 14 years after.
Yeah.
And my question was related to like path after undergrad. I know that maybe in astrophysics it's kind of like obvious that you have to do PhD and there are not so many options in industry, but like maybe for some folks who want to do like some more applied stuff closer to like engineering type of thing or like research and I don't know, like technology or something like that. What are your thoughts on going into industry right after undergrad and then maybe coming back to PhD? Is it something that you think is worth doing or would you like not suggest not wasting time and stuff like that?
So
Thanks.
I know, yeah, so that's a very good question. I'm going to talk a lot more about like the specifics of graduate school, but I'm probably not going to touch so much on that question. So I'm glad that you asked it. A lot of places, or at least, a substantial fraction of industry type jobs will oftentimes pay for you to go back and get higher degrees. So places like I've heard of this happening at places like Ball Aerospace. So it's an aerospace company out in Boulder. And a lot of those uh, those sorts of positions, you often have the opportunity to go back and do it. Um, you know, I kind of just stuck with my trajectory, just doing all of the education in one shot and then getting into research. And to be honest, I never really even knew what I wanted to do, if I'm being completely honest. Like I just kind of knew I like to solve problems, and astrophysics was really fun and that's what I was interested in, and I wanted to keep doing that. Um, but I think there is there's like a kind of a mental barrier that gets put up as you spend less and less time in an academic setting, just from the standpoint of learning new material, I think. And again, I don't have that personal experience, but I've heard a number of people say that, just that it's harder to go back to school just to get your mindset back into kind of learn mode and not do my job mode, if that sort of makes sense. So, um, yeah, I don't think I have any specific suggestions as to like whether you should or should not do that. It's kind of it's obviously it's up to you. Especially if if you know what you want to do and it doesn't necessarily require a PhD, then by all means, I think it makes sense to go straight into the job that you want, especially obviously if you can get it. um, I just know, like, going, especially if you want to end up at a major like research university, like somewhere like Lehigh or somewhere like Syracuse or bigger, something like Berkeley or whatever, you absolutely need to have a PhD, and you also need to have what's called postdoc experience. And I just, I was kind of just thinking along the lines of like maybe that's something I want to do one day, and I kind of just pushed myself into just getting it all kind of done in a sense. Um, at least the school part of it. And I'll talk a little bit about what I mean by that in the grad school discussion. But I don't know. I feel like I didn't really answer your question. And I'm sorry, I don't have a better answer for you. But that's kind of what I got.
No, you're good. Thank you so much for
Yeah.
your advice.
Yeah. So if there's nothing else immediately, I can talk about kind of grad school, because I think probably people who are listening are at the undergrad level and thinking about going to grad school, or are at the graduate level and not too far along in the career. And so I think I have, some useful suggestions and things to think about when you're at that career stage. So let me go back to screen sharing. Okay, right. So following my graduation from Lehigh in 2011, I moved out to the University of Colorado Boulder, where I pursued my PhD. And one of the things that you kind of get along the way is your master's. But before I get to the actual grad school experience, kind of considering grad school, if you're kind of thinking about it, so a few reasons that you may want to choose to go to grad school is if you really like solving problems. So as I mentioned, astrophysics is kind of the thing I'm really most interested in. But in general, I really just like solving problems. Something that really fascinates me, I think, because it's close to fluid dynamics, which is most of what I do, is actually traffic. For a while, I was actually commuting between Eastern Pennsylvania and Princeton when I was there as a postdoc. And so I was constantly dealing with the traffic on 78, and I would just think about it all the time, about how the dynamics of how traffic works. And it was kind of just a fascinating thing to think about trying to model. And in general, when you go on and you do a PhD or even a master's, what it demonstrates is that you can solve problems. That's effectively what you're doing en route to getting your PhD. And that skill is valuable to anyone, including any sort of employer who might hire you down the line, right? And so this gets back to your question that you asked me before, right? This is something useful irrespective of where you land in your career. If you're really, really passionate about it, right, inquisitive about science, for those of you that I'm speaking to now, or really whatever, learning on your own is something that I kind of alluded to. It's something that you might not be too familiar with, again, because the educational system, at least in the United States, we still kind of adhere to this very structured format where professors kind of know all the information and we're giving it to you in this prepackaged form. But learning on your own is kind of a skill that you need to have, I think, at least in my experiences, to be able to succeed in grad school. And if you really like to do that, you can use that skill very effectively when you're there. One of the things about research, and I'll get back to this a little bit, is that it can be really hard, and it's a very different experience from what you're used to. And you really need a lot of tenacity, and you really got to be dedicated to what you're doing in order to solve these problems, because essentially they're problems that no one has ever solved before. And so you really have to kind of have this sense of really never wanting to give up on solving a problem. And I mean, my own experience with this is problems in grad school, I still think about that I haven't really solved to the degree that I want to. And part of the reason for that is this kind of this funny irony about science, which is the more you do it, the less you feel like you actually understand, because in the process of solving one problem, you uncover, 10 or so other problems that you don't know the answer to and you don't know how to solve yet. And so it's really, just kind of important to, I don't know, just be resilient, dedicated, and really just want to solve the problems that you're interested in. And it's important to note that this is not quite the same as being a perfectionist. So getting things absolutely perfect is actually almost antithetical a little bit to at least science from a practical standpoint. And this also goes against what your kind of intuition tells you, because you've probably been educated in the same way that I was, which is that you want to get 100% on every single exam that you take. You want to get no points off, right? You want to get perfect homework assignments every single time. And that's fine. But in science, what you'll find very quickly is that you just want the damn thing to work. It doesn't have to be perfect. You just need your experiment or whatever it is to give you the result that you're after, or even just to show you why you're wrong. And so, again, this just goes back to being just tenacious about some of this stuff. And then, so this actually applied to me. So many of you probably may have student loans. So I had student loans too, coming out of undergrad. A fraction of your student loans can be what's called subsidized, which means that they don't actually accrue interest as long as you stay in school. And so for me, that was really valuable, because some of my student loans I could kind of keep and know that they weren't just accumulating in dollar amounts, while I could pay off the other ones that I knew were accruing interest. And then, there's also reasons you might not want to choose to go to graduate school. One of the things, and again, this goes back to the question you asked me, right? If you want a permanent job straight out of undergrad, if you kind of think about the timeline that I was talking about, I started at Lehigh in 2007, and it wasn't until 2020 that I really got what you might call a permanent job. So that's 13 years of school/research. And so if that's not the sort of time that you want to dedicate, you might want to think about something other than grad school. Moving and just going from place to place is kind of a necessary aspect of it. And again, a lot of this stuff I didn't know at the time. And if someone had told me this, I like would have thought about it more. I'm glad that I didn't. And so, don't let me deter you by any means. I'm just kind of giving you some advice. But I moved probably, I mean, at least like 7 times in the process of, going to Lehigh, then going to grad school, then going to my postdocs, and then moving to other postdocs. And so it can get really tiring, especially if you have a partner who has their own career to think about. I was lucky in that sense. My wife is actually a physical therapist, and physical therapy jobs are kind of ubiquitous. That's not to say that that's not hard to get them, obviously, but she was at least more I don't know, able to be more easily placed than I was. You just like traveling. So this also applied to me at first, right? I mean, I wanted to stay relatively local. But as part of this job, you end up having to go places and give talks, especially in grad school, you want to go to conferences. So that's something that you kind of need to do. An important part about grad school, and this can be kind of like jarring, is that grad school is really not just advanced undergrad. And so the first like couple of years, you are kind of just taking more classes. And in a sense, it is a continuation. But after that, it really gets into research. And so like, again, this goes back to kind of the passionate thing that I was talking about earlier. Like you really have to want it. And you really have to want to independently kind of discover some of this stuff. And at the end of the day, nobody knows the answer to the question that you're looking for. You're not going to find it in a textbook. And that's kind of the point of the research. So, if you're just thinking, I just want to take more classes, be cautious, I would say, because I know people who had that mindset and then didn't end up getting all the way to the end, unfortunately. You want to make a lot of money. Grad school, you get paid as a graduate student, which is actually different from other humanities, but it's not a lot of money. So, if making a huge buck straight out of undergrad is where your head is at, then grad school is not where you're gonna get that, at least not immediately. And finally, so this is also something I never would have expected. So one of like the main things that I actually do as a scientist is actually write. And that goes against your kind of like classic picture of a scientist of somebody standing at a blackboard scribbling down equations. But like 2 of the biggest things that I do are actually write and give talks. And so those are skills that, you might not be too familiar with, or you might not be super adept at right now necessarily, but you also get better at it. But this is the sort of thing where like, if you really, really hate writing or you really hate giving talks, like that's just an additional hurdle that you're going to have to get over when it comes down to it. Okay, so I'm not trying to deter anyone. I don't want to scare anybody. These are just kind of things to sort of think about if you're contemplating going to grad school. So some of you might be in the position of where you're thinking about applying to grad school, or maybe you already have recently and you're waiting to hear back at this point. So between kind of your junior and senior year, and probably maybe even a little bit before that, you can think about where you want to go to grad school. And you can, various things, geographic location, for example, can kind of influence where you want to go. But it's also totally fine to go to places beforehand, right? Even before you apply, just to visit and talk to the professors there. You want to look for places that have what you want to do research-wise. And so when I was an undergraduate student, the 2 things that I thought were really fascinating were relativity and quantum mechanics. And in an astrophysical sense, I really wanted to do something like high energy. And I knew also that I really like to do analytic theory. And so where I ended up going, and my advisor in graduate school, that was a lot of what he did. He did kind of analytical. So my grad school advisor is Mitch Biegelman. And he did a lot of analytic work that I was really attracted to and really liked. And so you want to, because research is, as I'll get to in a second, is going to be your life for a little while. And so you have to make sure that you love it and it's really what you want to do. And as with, most things, the, graduate admissions, everything just gets more competitive somehow. And so it's good to kind of apply broadly. apply to many of these things. I think when I was an undergrad, I applied to like, I don't know, 20 or so places. And for some of you, right, this can represent a financial burden. And a lot of places actually have application fee waivers. And so you can always ask about that and send, excuse me, send people emails. As I kind of mentioned at the beginning, when you start thinking about going to grad school, you're probably, and I'm not going to say this applies unilaterally to everyone, but you're probably relatively unfettered in terms of your constraints. And so you can really think about going even abroad. So like University of Cambridge, for example, in England, right, has a fantastic astronomy program. A lot of places in Europe have really fantastic programs. So like, as I said, I went to Colorado, and then I moved farther west to Berkeley. And so this is, something you can keep in mind. And then, ideally, after you apply, you get into a few places, and it's really critical that you visit, right? So when you get into grad school, a graduate school, if you're choosing between places, you really want to make sure that you go and you visit and you check it out and you talk to, especially the people that you want to work with, and make sure that it's like, of course, it's hard to tell on first impressions, right? But you want to make sure that you're not getting into something that you're pretty sure you're going to absolutely loathe, right, the moment that you get there. And so when you visit, talk to the current students, again, along the lines of having a life, see what they do for fun. And then you can talk about what are called quals or qualifying exams or comprehensive exams, which I'll get to in a couple of slides. Okay, are there any questions about this stuff? So like applying to grad school and everything? So I feel like this is kind of the precursor to what I want to just discuss.
Yeah, I did have a question. How much did you reach out to instructors and talk to them? Because whenever I was applying this past semester, I reached out to a few, but only like one or two of the ones that I reached out to actually responded. So I wasn't sure how effective it was really. Maybe it was different whenever you were applying.
I think it doesn't hurt, and I think it does make your name memorable. So like I wasn't on the graduate admissions committee this year in our physics department. I have been in the past. And as I said, right, this just gets increasingly competitive. And so there are a lot of applications you have to sift through. And if you reach out to someone and say, hey, I'm really interested in working with you during my graduate school career, are you taking on new researchers? Can you just tell me about your research? And, I'm thinking, I could potentially visit or something. It'd be great to just talk to you. It's unfortunate that whoever you reached out to didn't respond. I will tell you, especially in the fall around that time, we kind of start to get peppered with a lot of questions like that, which is not to say you shouldn't do it. But it's entirely possible that whoever you emailed saw it, meant to get back to it, and then legitimately forgot to,
Mhm.
But I think it is a good idea to reach out to people beforehand and talk to them. Like, for example, I can remember like I drove out to Penn State because that was one of the places I was really thinking about going. And I talked to, I think, Kevin Luman when I was there. And I just kind of got an idea of what the Penn State campus was like, and it was a fun, kind of day trip that we did. But I do think it's important to do that. Yeah.
Okay.
Any other questions? Okay. Okay. So in terms of like graduate school itself, as I kind of mentioned, years 1 and 2, your first couple of years in grad school are more about classes, and it despite what I said earlier, it is kind of a continuation of undergrad. And so I went to University of Colorado Boulder. At CU Boulder, there's actually a relatively large number of classes that you're required to take relative to other graduate programs. I think it amounts to something like 11 classes and then 4 1-credit seminars that you have to take. And then at the time, I really kind of despised that. because I kind of, wanted to get more into research at that point. But looking back, it was actually really beneficial for me, because as I mentioned, especially with Ginny having arrived around the same time that I did, she was able to offer some more classes that I wouldn't have had the opportunity to take. But there was a lot of phenomenology that I still had to learn, and so that was really useful to me. But just like undergrad, right, it's important to have a life. And this is why I said on the previous slide, get to know the graduate students in the program. And so what I did when I lived in Colorado, I lived with 4 other classmates in this big house in South Boulder. I kind of got into running a little bit. Played a lot more ultimate frisbee, learned how to homebrew. I played a lot more disc golf. I got a couple cats who still live with me today. One of them was meowing a little while ago. And I got married in 2013. And so again, it's important to just make sure that you're a human being, and you're kind of getting the necessary breaks when you need them from academic life. This is something that, I don't think I've ever encountered anyone who actually does this, but some people adopt the mentality of like just kind of bearing down, gritting their teeth, and getting through all of this. But I wouldn't recommend you do that. It's important to really have a personal life and hobbies, right, while you're also trying to finish your degree. So qualifying exams, I actually don't even know what Lehigh calls them, but here we call them quals. At Lehigh or in Boulder, we call them comps. So comps, comprehensive exams. Usually it's a written exam. Sometimes I think Lehigh does a combination of written and oral, if I remember correctly. Usually the material is kind of on 4 to 5, what you call core classes. Nowadays, I think a lot of places have, especially in astronomy, have gotten rid of this. It's kind of just like I don't know, an endurance test almost. For us at CU, it was like an all-day thing where from like 9 to 12, you worked on like the first 2 questions, and then you had like a half-hour lunch break, and then from like 12:30 to 5, you worked on like the remaining 3 questions, right? And by questions, I of course mean like multi-part, enormous questions based on whatever subject they were supposed to be about. And it's designed to sort of test your understanding to some extent, but there's really, I don't know, there are a lot of problems with these enormous tests like this, and a lot of places, especially with COVID, have kind of just gotten away from it. We still have ours here. We always fight about getting rid of it, and who knows. And during those the first 1 to 2 years, it's also really important to start thinking about research and finding an advisor. And so I kind of knew who I wanted to work with. And I was lucky that he was willing to sort of take me on at the beginning. But usually, especially here, during your first summer is kind of where you want to find a first like research project and an advisor who's willing to work with you. So those are your first couple of years. And then from years 2 to what I would say is N, where N is some number on the order of 5 to 6 years. That's when you're about to finish and defend your thesis. Your life and the things that you focus on, research itself, it's just very, very different or probably very different from what you had experienced during undergrad and during those first 1 to 2 years of graduate school, because research is really kind of a nebulous thing. I was thinking about it when I was writing the slide, like how would I actually define this? And I think like there's a couple different ways, things you could say. You can think about it as kind of coming up with some new theory or some new type of model that can be as sophisticated or not as you want to try to explain something. And so in astronomy, astronomy has always been and will forever be just an observationally driven field, because we're just not clever enough to figure out what the universe is doing before it shows us. And so we observe something really crazy and we're like, what sort of physics is at play to explain that really weird thing? So that's like, coming up with a model, or it might be designing some kind of an experiment, right? And so this is obviously not necessarily in astronomy, right? You want to design an experiment to test something. Or just like, trying to just solve a problem, like a problem that may not even be all that well known, or that's a very well known problem with some new kind of method that you develop. And I would say that I kind of do all three of these things. I really like the latter one. As I said, I really like to solve problems, and I really like to think for a while about hard problems. It's just, I don't know, maybe I'm just kind of a masochist or something, but it's like, something I like to do. Um, but I also like to think about, like, I work often with what we call observers, people who actually take observations, right? And who use professional instruments to take observations of astronomical phenomena. I work with people to try to explain things, and I like that too. And then one of the things that again, I'm a theorist, but also oftentimes when you're coming up with a method to solve a problem, you have to make some set of approximations. Um, and one of the ways you can kind of test that is to run what's called a numerical experiment. And so you can get a computer, if you're clever about it, to solve your problem, and simultaneously relax assumptions that go into it. And usually what that means is that the result that you get out from your computation is less general than the model itself that you're proposing, but it's one way to test what you're doing. And so all of these are simultaneously research, and depending on which field you're in, these things might differ somewhat. In the humanities, it might be very different. But in science anyway, I think this is a fairly good description of what research is actually about. And it's hard. Because as I said, it's very different from classroom learning. You really have to be dedicated, determined, and in some sense, like obsessed. And as I said, there are problems I still think about from grad school that I haven't solved. And I was talking with a friend of mine, and it's kind of like there comes a point in your life, I said before I played like Smash Brothers or whatever. But there comes a point in your life when you actually are so obsessed with solving some problem that you actually choose research over your video games. That's like, the kind of level of obsession that I'm talking about. And this is really overwhelming, especially at the beginning, because at the beginning, you talk to your advisor, and your advisor says, go read these 10 papers. And in the process of reading those 10 papers, you read the first paragraph of the first one, and there are like 20 different words you don't know the meaning of. And so you have to go look at all the papers that are referred to in that first paragraph. And it just quickly becomes this like binary tree that gets enormous. And it really seems like, how can you possibly do anything new? Everybody already knows everything. But this comes with time, right? And so eventually it gets easier to kind of figure out the problems and see the new avenues and kind of creative ways to solve problems, but it's definitely still hard. And so, I would by no means say that research is easy, even at, the professor level, right? It can still be very like just frustrating. Like, why isn't this thing working, right? And for the same reason, it can be depressing, right? It's like, God, I'm like wasting so much time. Like, what the heck's going on? But that's kind of the I don't know, the nuts and bolts of research. And at some point you'll probably have to TA. But I would sort of suggest that if you're thinking about going the academic route in a research heavy institution, or if you're thinking about doing something in industry, this isn't really where you want to focus most of your time. And in general, like when you're doing this, have a life, right? Make sure you do things, make sure you go out and enjoy your time, because again, this is like one of the times in your life where you're going to have probably the most freedom. But at the same time, don't like surround yourself with distractions, is the way that I would say it. And there's kind of this phrase where it's something like, when it comes time to write your thesis, suddenly your room and your entire house becomes very clean. And what that means is that you're saying like, God, I have to write my thesis, but I really don't want to. And then you're like, oh, but I got that pile of laundry over there. That really needs to get done. I should go do that. And you're like, oh, well, I also need to like clean my windows. They look disgusting. I should go do that. Right. And so you're kind of like intentionally distracting yourself and doing everything possible, but the thing that really needs to get done. Okay. And so that's like a very natural thing to do. It's effectively procrastinating. And try not to do that, but obviously to some extent, everyone does it. So, as I mentioned, so research really requires writing, and it's the number one thing that I do. And that probably, I mean, it would have come as a very big shock to me as I was sitting in your seat 10, however many years ago now. It's not something that you expect. And scientific writing is actually very different from, writing you would have done in your 12th grade English class or something. And the way to really learn how to do this is to read papers. And so if you haven't heard of it, there's something called the archive. So the archive is what's called a preprint server. So when you go through the process of publishing a paper, you realize that it's agonizingly slow to actually go from step one of just submitting the paper and then finally getting it published. And so a preprint server is basically a place where you can put your results and specifically your papers without it having necessarily been accepted for publication yet. And so if you go to this thing called the archive, so the specific physics and /new, those are the new papers that will appear every single day. And usually there's on the order of like 50 of them. And so it's just a good kind of repository where you can see scientific writing kind of in action. And you know, writing is kind of like telling a story, and you want to kind of have like a theme, and you want to spell out the problem that you're setting out to solve. You want to kind of tell the backstory, give your conclusions, you know, describe your methodology, and then summarize, right? And so it's very much like telling a story. The second thing research requires is giving talks. And so writing is one way to disseminate your results. The other way is actually to give presentations. And also in grad school, you might have something like an oral qualifying exam. At CU, we call this Comps 2. At Syracuse, we call it the research oral. And it's essentially kind of like a way for you to demonstrate that you're on some trajectory toward doing research, because that's actually mainly the point of years 2 through N when you're in graduate school. And just like writing, giving talks is like telling a story. And just to give you some kind of pointers, people really care about the results, not the methods that you used to do whatever you did. And I put sadly in parentheses here because the method is actually what your life is for the most part. Eventually you arrive at the results, but you've spent like, you know, a tremendous amount of time trying to figure out how to get that result. And the fact is people don't care. They just want to know what the result is, because that's the thing that they can appreciate most readily. Just don't put math on slides. It just immediately loses everyone's attention. And don't put too many words on slides. So what I'm doing right now, don't do when you're giving a scientific talk. I think this is slightly different because I actually would happily give you all these slides. And, you know, if there's somewhere I can upload these, I'm happy to do that. But, you know, if you do use words, do kind of the thing that I'm doing, which is where you put everything in bullet points and you don't just blast it all up there on the screen at once. You kind of just walk everybody through step by step. And then kind of the last big point about this years 2 through N and doing research is that it requires money. So as I said, you get paid as a graduate student, but your advisor will be the one who's paying you. This actually isn't necessarily the way it works overseas. But in the United States, the way it works is that for a research position, your advisor is the one who actually has to put up the money to pay you to do the research. And if that doesn't happen, you end up having to TA. And so the way that I get money to support the graduate students I work with today is that I write proposals. And so that's basically like in some cases, very big document that says, here's all the amazing research that I want to do, but I can't do it because I don't have any money, so you should give me some money. And, you know, it takes a lot of time. It's one of the reasons that I write so much. But you can actually, as a graduate student, you can actually apply for money yourself. You can apply for your own money. A couple of options are the NSF GRFP. So this is the Graduate Research Fellowship Program. I don't know if you might have heard of this. You're actually eligible to apply for this, I think technically anytime during your undergrad, but realistically, it's effectively in your senior year. And sometime over the past decade or so, they changed this slightly from what I was used to. Nowadays, you can apply for this in years 1 or year 2 of graduate school. So you've only got one shot as a graduate student. Another one in astrophysics is called the FINEST. I forget what the FINEST acronym stands for, but it's kind of equivalent to the GRFP, but it's from NASA instead of NSF. The difference is that you can apply for this at any time as a graduate student, and it funds you for 1 to 3 years. These things are really hard to get. I applied for these every single year when I was a grad student. I never got one, but it's really, really good preparation, actually. It's preparation for doing this when you start to apply for postdoc applications, and it's very good preparation, especially as like a professor, right? When you're applying for these things more regularly. And as I said, this is part of the reason that I write so much. Are there any questions on stuff that I said so far, or on stuff that I said between the last break and now?
I did have I guess a little question. Is this like your process with applying for funding and stuff like that? Is it similar for fellowships? and things. I know not all fellowships you have to apply for, some they just give to you, but like the ones that you got, was it like a similar process where you had to, I don't know, justify why you should get the fellowship and
Yeah,
everything?
the distinction between like, or the precise definition of fellowship, I'm not even really sure of. So the GRFP stands for Graduate Research Fellowship Program.
Right.
So the GRFP, like you become a GRF or a Graduate Research Fellow, right, by winning one of these things. But what I'm really talking about pertains to all of those. And so the finessed, it's like Future Investigators of NASA, Earth and Space Science Technology, something like that. Um, so I guess you could call that a fellowship. I think technically maybe it's not, but it's exactly the same sort of principle. And so the idea is you write up so for the GRFP, it's really short. It's like 2 pages, your research statement or your research proposal. For the finesse, it's 6 pages. So you got a little bit more space. You kind of write about what you want to do over the next, in the case of the finesse, it's anywhere from 1 to 3 years. And it's a different skill slightly than just writing a paper. And it also kind of requires you to think slightly differently because you need to kind of like you need to show that you're capable of doing the research that you're proposing. And one of the ways to do that is to give what you call preliminary results. But you also don't want to kind of like have already done all the research because then why are they going to give you any money, right? But anyway, to answer your question, yeah, fellowships and these sorts of things are effectively the same. It's the one difference is as you get to more advanced stages of your career, they get to be more annoying in both in terms of the length requirements and in terms of the other extraneous materials that they require. And so it's not just what you might call the project description, which is the actual science that you need to submit. It's also a bunch of other forms. And thankfully, especially for the GRFP and the finesse, those things aren't too burdensome. They also aren't non-existent. But yeah, they're all kind of very, very similar things.
Okay.
Yeah. Are there other questions? Okay. So as you continue on through research, eventually you get to years n-1 to n, where again, n is on the order of 5 to 6 is the total number of years that you'll spend in graduate school, which is when you start thinking about finishing up. And during that time, you have to write your thesis. And so in science, at least in astronomy and physics, this depends a little bit on what you do. So if you work like on designing an experiment for like your entire graduate school career, then it's not quite what I'm going to describe. But I remember asking, it wasn't my advisor, it was actually Phil Armitage, who was another professor at Colorado at the time. He's now at Stony Brook. I think I said to him, so I'm like thinking about my thesis, I got to defend soon. Should I just staple my papers together? And he responded by saying yes. And so what I mean by that is that throughout your career, your grad school career, what you do is you write papers that describe your scientific results. And that's a lot of words that you put on paper. And so your thesis really, like, you don't want to reinvent all the science and just do an extra whole bunch of science again, because like that's what you've been doing the whole time. And so by the time you get to the point where you're ready to graduate, it really does come down to putting all your papers together in some LaTeX class file that your university will provide for you, writing an introduction, writing a conclusion, and that's it. You then defend your thesis, and this is actually really fun because at this point, like, remember, like I said in the beginning, it's really daunting because you don't understand it. You don't know anything. Everybody else knows everything. But by the time you're ready to defend, you're like the absolute expert on what you're doing. Like nobody knows this stuff better than you do. And this is actually fun, right? You get to like stand up and say like, here's all the crap that I did over the past 10 years. And it's really cool to talk about all the science that you do. And then it's again, I'm saying all of this with an academic trajectory in mind. So at that point, it becomes time to apply for what are called postdocs. And so when I was an undergraduate student, I didn't even know what a postdoc was. A postdoc is, it stands for after you get your doctorate. It's effectively kind of like a semi-independent research position, so similar to what you were doing in grad school, but with more independence and at usually some other institution from where you did your graduate degree. And kind of the plan or the purpose of this is to demonstrate that you can do research at a more independent level and with other people. And again, speaking specifically to astronomy, you can go to what's called the AAS job register. And you at the AAS job register, there will be a list of, I don't know, 50 to 100 postdoc positions that are available for you to apply to. And so the other day I went on the AAS job register, I picked one out. Okay, this is like typical-ish of what you'll see, right? So it's looking at disks around supermassive black holes in this case, and then kind of describes all the stuff that you need to do. And so among the documents you need to submit are kind of your research experience. And usually they have, so this one I think is slightly more tailored to like a specific project that the PI in this case wants to do. But sometimes it's more, or it's less specific. And so they'll just ask for something like a research statement. And then it's not really clear exactly what the heck that they want. But you kind of just can describe what you kind of plan to do or what you'd like to do over the next 3 years that you would be in this position. And so the kind of advice that I would give for this is the same that I said for grad schools. There are many opportunities, apply to many of these things. I've probably applied to like, I don't know, it's probably something like 20 to 30 of these things. So as Daniel asked, right, fellowships, there are opportunities, postdoc fellowship opportunities. So NSF has one. So this is the Astronomy and Astrophysics Postdoctoral Fellowship, the Hubble Fellowship, and then there are also kind of university-specific ones. And I just listed a few of them here. So the Lyman Spitzer is at Princeton. Princeton also has like 2 or 3 other ones. There's the Burke Fellowship, which is at Caltech. Berkeley has the Miller Fellowship, which is kind of unique in terms of the application materials you have to submit. And then there's the TAC, the Theoretical Astrophysics Center Fellowship, the Papalardo at MIT, and then the Institute for Theory and Computation, ITC Fellowship at Harvard. And then there's a question that just came up in the chat, apparently. Are there any fees to apply? No, there aren't. Usually not, I should say. In fact, if there was a fee, I'd be really surprised and kind of annoyed. So yeah, usually not. So I just talked a lot about grad school, and I spent most of my time talking about that because I think that is a big chunk of your career, and it's also where you kind of have to make the most drastic changes, I guess, in the way that you think about how education and research works. You really have to come to grips with what research really is, and that can be pretty daunting. And so I kind of wanted to just talk about the various aspects of that. But I'm happy to. I only have like a couple more slides because I really wasn't going to say too much about postdocs. But if there are any questions or just like other, I don't know, points of discussion.
Okay, I have a question. Is Syracuse worth going for graduate school?
Well, it depends on what you want to do. So what are you interested in?
I'm interested in soft matter, and I am accepted by Syracuse.
Okay, yeah. So are you thinking are you doing theory? So like Chris Santangelo or Joey?
Not sure.
Yeah. So it's like soft matter. I mean, soft matter is something that is actually, this is another thing that really kind of fascinates me. So I'm not, but I mean, I'm very, very far from an expert in what they do. I think it's really, really cool. But I think soft matter in general is kind of, I don't know like how pervasive that is in terms of where you can get it at the graduate level. And I know that like Chris Santangelo and Joey Paulson are very, very good at what they do. Theoretical and experimental, it kind of respectively is what they do. So, I mean, I can, talk more about our specific PhD program, but actually, so if you were accepted to come, you're accepted? Is that what you said?
I have not decided, but
but you were accepted.
Yeah.
Yeah, so then you should come to the graduate visitation. So
Yeah.
that's like March 24th, I think.
Is soft matter somehow related to your traffic problem?
Maybe if there's an accident.
Okay, thank you.
Yeah, I mean, yeah, I would, you know, take my advice that I said earlier and come check out the campus and come talk to Chris and Joey and kind of see what the place is like. I think it's great. I think it's a really fantastic institution. And I think we have a very diverse set of interests when it comes to the physics that we do. And so I think you'll have a lot of opportunities to kind of look at other potential disciplines you might want to focus in if you're not quite sure what you want to do yet. That was something else actually I didn't really say. I mean, I said to think about what you want to do, but it's also not good to like pigeonhole yourself necessarily. Like you don't want to be too specific about the thing that you want to do because there's a lot of stuff to learn out there. And so like as I said in astronomy, what I really was interested in was doing analytic theory and like high energy explosive relativistic stuff. But I don't really care exactly what it was. And so now I work on so something called the tidal disruption events, which is where you tidally destroy a star by a black hole, and that creates an accretion flow. But they can also launch relativistic jets. And so I've worked a lot on trying to understand the interaction between a relativistic jet and a surrounding medium. I'm also like just obsessed with understanding what are called shock waves, for which there actually are analogs in traffic. But shock waves are kind of a natural consequence of any sort of explosive injection of energy into some medium effectively. And so I kind of work on a smattering of things now just because I kind of have interests that are all over the place. But in general, that's kind of a good, I think, mentality to have, is to kind of know what you want to do, but not exactly what you want to do. If that makes sense.
Okay, thank you so much.
Yeah.
I had a question real quick.
Yeah, go for it.
I guess first of all, I'll just say I set the meeting to end, or I set the end time to 9:15. I don't know if that'll mean it'll cut off exactly. So if
Okay.
we just drop, know that we didn't cut you off in the middle of talking or anything. Um, but I know you said to apply to a lot of postdocs. Did you have, I guess, other than maybe astrophysics related to special relativity and stuff like that, did you have any criteria on choosing which postdocs to apply for and which you thought would be worth your time or your experience and all that?
Sure. Yeah, that's a good question. So a lot of the ones, so when I applied the first time, I was still, I wasn't, I guess, really expecting to do as well on the postdoc market as I ended up doing. And so I was more selective as to what I applied to. And I really focused more on independent positions. And so this kind of actually gets into what I was going to say on my next slide. So like one of the things you want to do in a postdoc is kind of demonstrate that you're more independent and it wasn't just kind of your advisor just, standing over you typing on the keyboard the whole time, right? So when I was applying, so things like the Hubble that I mentioned on the previous slide. So when I was applying for this, actually, it was in 2015. The Hubble and the Einstein Fellowship were actually two different things. So that's actually the reason that I was able to actually get two of them, is because I won the Einstein as in 2015 when it was separate from the Hubble, and then I was lucky enough to get the Hubble when it was actually now unified with the Einstein. So the Hubble, the NSF, AAPF, and a lot of these sort of like prize fellowships, people call them, are independent from the standpoint that they okay, so for the AAPF and for the Hubble, you submit a research proposal effectively, right? It's you submit a proposal and you say, this is what I want to do over the duration of this fellowship. For these ones, you effectively do the same thing. The Miller, as I said, is different. The Miller is kind of strange. But the TAC, the Papalardo, all this stuff, you basically say like, this is the research that I think is really interesting and that I think is groundbreaking and whatever for various reasons and that I really want to do. And if you get one of these things, then in principle, you know what you want to do and you just go off and do it. And so that, can be daunting at first because, again, you're kind of like leaving the next nest. It's kind of all on you at that point. And so I got one of these things straight out of grad school, which, as I said, I was not really expecting. And for me, again, I got kind of lucky because I ended up working with or getting to work with a really fantastic advisor at the postdoc level who's LA Quadert. And so he, at the time, was at Berkeley. He's now actually at Princeton. But, it wasn't the same type of, I mean, it's less about like, go do this thing. It's more just kind of like discussing at a much higher level what sort of problems are interesting and what other areas exist to go into in terms of subfields, really. And so like when I started working with Elliot, I had done a lot on tidal disruption events, but then I really started getting more interested in like weak explosions. And so terminal states of massive stars that are not actually successful supernovae. And this is something I still think about a lot. And so, yeah, so I applied to a lot of these more independent positions. And that was kind of what I restricted myself to for the most part. I think if I recall correctly, but there are also, so like the job ad that I was showing you here. So it says here, the project is attacking the questions of disks around supermassive black holes using hydro simulations to measure how accretion rates work, right? That's like a very specific thing that this person, the PI here, wants this postdoctoral researcher to do, right? And so this is kind of the other, I would say, close to like extreme, where there's a very well-defined project that the person wants to be done. And so, it's kind of like up to you to some extent, to decide if this is like the thing you really are interested in, the thing you want to do, then like absolutely, right, you should go apply for that. But when I was applying, I kind of, I don't know, I had a sense of what I wanted to focus on and what I thought was really interesting, and I must have applied for like a few that were more. Actually, another one that's on here, then I'll just put it down just because I know you're recording here. This is the Yale YCAA is another one. Yeah, so I guess I was kind of selective in what I was applying for it. But that being said, there are many of these things, right? And a lot of them are at many of these kind of prestigious institutions across the country. And then there's ones that, there's ones overseas too. Like, so Cambridge, University of Cambridge, Oxford has some that you can be eligible for. So
Okay, yeah, thank you. And if you want to send me this slideshow, I can upload it so that I can share it with everybody too, so that they have access to all this stuff.
yeah, absolutely.
Awesome.
Yeah, I didn't really have too much else, The one thing I do want to just end on, I guess, in terms of the last thing that I'll say, unless there are more questions, is all of what I've kind of been saying is specific to like the, academic trajectory that I had, because that's what I know. But, a lot of the career stages and a lot of the training that you get at these various career stages is valuable to pretty much any employer. And the one specific example that I have, somebody called me from this company called Citadel Securities. So it's like a hedge fund type of thing. And the guy basically said the same thing that I said earlier, which is that you just can't give up on a problem. And what he was saying was like, we want you to try to solve a problem 100 different ways. And like, if 99 out of 100 don't work, that's fine. But what we want is the 100th one, So like that's sort of like insistence, and just an absolute obsession with like solving problems is like really, really valuable in kind of everywhere. So if you think like industry might be something you want to do, I wouldn't say that you absolutely shouldn't go to grad school, right? I think like grad school and even postdocs, like I know people that have done postdocs and then have then gone into industry and then have come back to academia. That actually happens more frequently than you might think. So, but yeah, if there's any other remaining questions or anything, I'm happy to discuss. I guess I can just stop sharing my screen.
Okay, I have another question. Which programming language do you think is most useful for physicists?
For physicists, I don't know if I could speak generally about physics. I think it's actually more about the research that you're doing. And so, you know, if you're doing like more engineering type of stuff, and so like some of the people in the physics department here actually design some of the detectors for LIGO, so which detects gravitational wave events. There, you know, I know that I think that they're pretty familiar with MATLAB, which is used a lot by engineers. I really like analytic theory, and symbolic manipulation is actually rare in terms of programming languages. And Mathematica is one of the only ones that really has like built-in tools to do a lot of what I need it to do. Which is why it's so useful for me. On the other hand, if you're, you know, if you're running like really heavy duty simulations, like, you know, on multiple nodes, so you're using like, you know, really serious heavy duty computation, a lot of programs, a lot of software is actually still written in Fortran and C, because it's so efficient, for various reasons. And so if you really want to if you really want to get into that, then you're going to have to learn at least the very basics of Fortran. And, you know, Python, I think, I don't know, I sort of feel like Python is just converging to Mathematica personally. But, you know, Python is much more, is kind of, I think it's easier in terms of the learning hurdles, and it is certainly, but at the same time, it has all the same basic syntax that pretty much every other language has. So I mean, I personally, I just love Mathematica because it has you know, of course it has its quirks, but there are also pieces of it that are extremely dependable, and that I use just like all the time. So I don't know. I think it depends on what you do. So if you work with like Chris Santangelo, right? If you want to do soft matter, I know Chris uses Mathematica all the time. So,
Okay, thank you so much.
yep.
All right. I don't think we have any more questions. So thank you so much for coming out.
Yep.
I appreciate it. We learned a lot. At least I did.
Yeah. And so I'm happy to send you the set of slides. I don't know what I guess I can just send it to you via email. That's probably because it's not a huge file. And then yeah, I hope to. I mean, it was really. Did Jenny like talk to you? Because like I just saw Jenny at AAS like 4 weeks ago, and then you coincidentally sent me that email. It was kind of. Did you?
Yeah, like we had talked, we had some event for physics majors during a lunch. Hey, when how could you mute your thing? Oh, sorry. Um, yeah, we were talking about I mentioned that I wanted to invite Lehigh alums to give a talk, and she thought that it was a good idea. And she actually is one of the people that gave me the most names. So she
Okay.
seems to be most in touch, I
Yeah.
think. Yeah, it was really cool that she was able to provide a bunch of people like that.
Yeah. Okay. Yeah, that's great. I just was like, this is a weird coincidence. Yeah, so hopefully, you know, sometime in the fall, I can come down, and I'd love to, you know, continue this discussion. And I mean, it sounds like you said you applied to grad schools and everything, right?
Yeah, so I mean, I got accepted into Lehigh. I might be able to stay and see
That's
your
fantastic.
colloquium.
Yeah,
See.
it's great. Yeah. So I'm happy. Yeah. Anyway, assuming that works and I can come down, I'm happy to, you know, have another discussion with all of you. It'd be great.
Yeah, that would definitely be cool to have something in person.
Yeah.
Well, thanks so much again. Have a good night.
Yeah.
Get some sleep, hopefully, with the twins and everybody. Keep
I'll
me
try.
Yeah,
Yeah.
thank you so much for the talk. It was super helpful.
Yep, you're welcome. So, all right, I will talk to all of you soon.
All right.